Welcome back. In this video, we are going to finish chapter 4 by covering the last section about connected components. As you know by now, not every topological space is connected. When it's not connected, it can be split into pieces. And these pieces, actually, these connected pieces are called the connected components of the space. Okay, so now, of course, we need to give a more precise definition. If you have a topological space X, we define a binary relation of X in the following way. 2 points X and Y, small x, small y, are related if there exists a connected subset of X containing both small x and small y. So now let us check quickly that this is really indeed an equivalence relation. So X is related to itself because the singleton X is connected, and symmetry should be clear as well. Transitivity is a little bit less clear. If X is related to Y and Y is related to Z, then by definition there exists a connected set capital A containing X and Y, and there exists a connected subset B of the space containing Y and Z. Then A union B is connected as a union of two connected sets having a common point, which is Y. So therefore, X and Z belong to A union B, which is connected. Therefore, X is related to Z. Now, any equivalence relation on a set partitions the set into equivalence classes. So the class containing an element is, by definition, the set of all points or elements that are in relation with this element. Okay? And so we know that two equivalence classes are either disjoint or identical, and the whole set is the union of the pairwise disjoint equivalence classes. So in the case of the relation that you just defined, the equivalence classes for this relation are called the connected components of the space, or just sometimes just components. Okay. Now, of course, when the space is connected, then all elements are related, actually, and there is just one equivalence class. So let us give, as usual, some examples. What are the connected components of R star? R star is not connected, but R star can be written as the disjoint union of two open intervals, -infinity 0 and 0 infinity. And these two are actually the biggest connected sets contained in R star. Okay, so these are the components. Okay, so any two negative numbers are related. So they belong to the same component -infinity 0, and any two positive numbers are related. So they belong to the same connected component 0 plus infinity. But a negative number and a positive number are not related. The connected components of Z are the singletons. Okay? Because, well, first of all, any singleton is connected, and it should be clear that any subset of Z containing more than one element is disconnected, as you may check easily. Okay, we did something similar for Q. Okay, so in general, a space whose components are the singletons and the empty set, of course, is said to be totally disconnected. Okay? So Q, we proved it earlier that Q is totally disconnected because the connected components of Q are the singletons. Now, of course, we don't consider the empty set as a connected component because it's empty. Okay. And of course, we said that we observed that a connected space has only one component, the space itself. So all elements are in relation. Now, let us record some basic properties of connected components. If you have a topological space X, then two connected components of the space are either disjoint or identical, and the whole space is a disjoint union of these components. Okay, so we have a partition of the space into components. And second property, the connected component containing an element, small x, is the biggest with respect to inclusion, is the biggest connected subset of x that contains x, as expected. So will denoted by C of x, or x between brackets, for a class, because it's really a class. The components of x are closed, but not necessarily open. And every non-empty connected subset of x is contained in exactly one component. Okay, so this is really straightforward. So let us, we already observed this because this is true for any equivalence relation. Now, second point, we have to prove that the connected component containing small x is the biggest connected set containing small x. Okay, so we consider the union of all connected sets of the space containing small x. Now, this, so call it d of x. Then we know from theorem 4.1 that d of x is connected indeed, because it's a union of connected set having a common point, which is small x. Okay, so now we'll prove that d of x is equal to c of x, so double inclusion. So we consider an element small y in this d of x. Then both x and y belong to the same connected set, which is d of x. So x is related to y. Okay? So therefore, y is in the class of x. Okay? So therefore, d of x is contained in c of x. Now conversely, if we take an element y in the component containing small x, then by definition y is related to x, so there exists a connected set capital A containing both x and y, but d of x is the union of all these connected. So in particular, d of x contains A. Okay? Since y is in A, then y is in d of x. So any element in c of x is in d of x. Okay? And therefore we have the reverse inclusion. And now, of course, the union of all connected sets containing small x is, of course, the biggest connected set. There's no bigger element, actually, with respect to inclusion. Okay? Because we exhausted all possible sets that contain connected set that contains small x. Okay, so the connected component containing a point is the biggest with respect to inclusion, biggest connected set containing the point. Now, third point. Why the components are closed? Okay, consider a component, C of x. It's an equivalence class. If so, since C of x is by definition connected, because it's the biggest connected set, its closure, as we know from lemma 4.2, the closure of connected set is connected. So the closure of Cx is connected. But by the previous point, C of x is the biggest connected set containing x. Therefore, C of x contains this connected set Cx bar. So Cx bar is contained in Cx. So I have equality. So the closure of Cx is equal to Cx, and therefore C of x is closed. So don't be confused. If you go back to the first example, the connected components of R star are minus infinity 0. Minus and 0 plus infinity. Minus infinity 0 actually is open in R, but it's not closed in R, but it's closed in R star. Okay? Why? Because its complement, which is 0 infinity open, is open in R star. Okay? So minus infinity 0 is both, is clopen actually. Okay? So it's both open and closed, not in R, but in R star. Okay, and last point. Yeah, so every connected set is contained in exactly one component, non-empty, of course. So if A is a non-empty connected set that containing one element, small x, then by definition, by point 2 actually, C of x is the biggest connected set containing small x. Therefore, C of x contains A, and A cannot be contained in another component because the components are disjoint. So, for example, if you go back to the first example of R star, if you consider the interval 1, 2 closed, let us say, Now, this is a connected set containing 1. And it's contained in which component? It's contained in the component 0 plus infinity. Okay. Okay, now remark, if X has finitely many components, then every connected component is necessarily open. Why? Because we said that the components are closed. Okay, so if we have finitely many components, let us say C1, Cn, the complement of C1 will be just C2, etc., Cn. And this is each one being closed, the union is closed. Therefore, the complement of C1 is closed, and therefore C1 is open as well. Okay. But the argument does not work if you have infinitely many components. Okay. And actually, you should pause the video and try to find an example of a set having infinitely many components, an R, if you like. You already know that, encountered that example of a set having infinitely many components. Okay. Now, but in general, components, as we said, need not be open. For example, the components of Q are not open in Q actually. But if capital O is an open subset of Rn, then the connected components of O are open. And we'll prove that actually by the end of the video. But if you like, try to think why this is true. Okay. Okay. Now, next result. What is the relation between connected components and homeomorphisms? If you have a homeomorphism, small f, between two spaces, x and y, then f takes components into components. So more precisely, the image under f of a connected component is the connected component containing f of x. So f of cx is c of fx. So in particular, the number of connected components of a space is what we call a topological invariant. So by now, you should be familiar with this notion of, already encountered it before, connectedness is a topological invariant. Yeah, because it's conserved under homeomorphisms. Okay, compactness is another topological invariant. Okay, so actually we can say that topology is the study of properties that survives when we apply a homomorphism. Okay, so when we deform, we can always think of a homomorphism as being a deformation of a space into another space. And so, but there are some properties of the first space that persist when we apply this transformation. Okay, so compactness is conserved even if the spaces look different, but they have some common topological properties. So compactness is conserved, connectedness is conserved, the number of connected components is conserved. Okay, so let us prove this equality. So how do we prove that? Double inclusion. So first of all, C of x is connected, and we know that the direct image under a continuous map of a connected set is connected. And since x belongs to C of x, then f of x belongs to f of C of x. So f of Cx is a connected subset containing f of x. But C of f of x is the biggest connected set containing f of x. Therefore, we have one inclusion. So f of Cx is contained in C of f of x. Now, conversely, take an element y in C of f of x. Now, every element y, because if f is a bijection, so y is the image of a certain element z. So y is equal to f of z, and therefore f of z belongs to this connected component containing. What does it mean that f of z is in the connected component containing f of x? It means that f of z and f of x are related, so they belong to the same connected set, which is actually C of f of x. Okay, so f of x and f of z belong to the same connected set C, and this means that z and x belongs to f minus 1 of C. But f minus 1 of C is the direct image under f minus 1 of a connected set, so it's connected. So x and z belong to the same connected set, and therefore they are related. So Z is in the class of Cx, of X. Okay, so therefore, Y, which is f of Z, belongs to the image of the connected component. Okay, because if Z belongs to f minus 1 of C, then f of Z belongs to C, which is C of f of X. Okay, so this concludes the proof of the simple result. Now let us illustrate the use of this theorem on certain examples that we always ask in the exams to test your understanding of this important notion of connectedness. So we said that one of the problems of topology is to distinguish between spaces. So we'd like to know, given two spaces, are they homomorphic or not? Okay. Now, of course, this problem can be very difficult, and in general, it requires advanced tools. But in some cases, we can use a connectedness argument to distinguish between spaces. So, for example, if you consider the straight line segment, this closed segment, the compact segment 0,1, and the unit circle S1. Now, both are compact, but they are not homomorphic. Now, this should be intuitively clear because we can deform 0,1, we can bend 0,1 and get a circle. But if you want to go back, we have to split the circle. So we don't have a homomorphism, but we can make this reasoning more precise by using a connectedness argument. What happens if you remove the middle point of 0,1? When we remove the middle point of 1/2 of 0,1, we get two connected components, which are 0,1/2 open and 1/2 1 open. Okay, so the resulting space has two connected components. Whereas if we remove any point from the circle, the resulting space remains connected. Okay, if we had a homomorphism between 0,1 and S1, then we would have a homomorphism between 0,1 without the middle point, its middle point, and the circle without a point, the punctured circle. But one space is connected, the other one is not connected, so it's impossible. Okay, so 0,1 and S1 cannot be homomorphic. Now, if you consider the shapes X and Y, okay, so X is just a shape, it's a letter, it's a compact subset of R2. Just take two straight lines and intersect them, okay? And Y is also a shape, actually. So are these shapes homomorphic? Okay, because no. Why? Because if we remove the central point of this shape X, what is the remaining space? It consists of 4 segments, so it has four connected components. Whereas if we remove a point from Y, okay, now it depends on the point that we remove, but if at the best, the resulting space, so the resulting space will have at most 3 connected components. It may have 1 component if we remove, for example, an extreme point, or even 2 components if we remove something. Okay, so if we remove a point from Y, you may get 1 component, 2 components, or maximum 3 components. Okay, but when we remove the middle point of X, we get 4 connected components. Okay, since 4 is different from 3, there can be no homomorphism from the shape X to the shape Y. Okay. The shapes A and plus infinity also are not homomorphic. I cannot find an ingenious transformation, continuous transformation that deforms A into plus infinity. Okay, why? Here, if we use the same argument and as in examples 1 and 2, we will not get a satisfying answer. But what if we remove the shape A actually contains a circle, a topological circle. So when we remove the circle from A triangle actually, because a triangle and the circle are the same, we get what? We get 2 straight line segments. So therefore, the resulting space contains 2 connected components. Whereas if we remove a topological circle from plus infinity, the resulting space is just a circle without a point. Okay, and clearly, the resulting space obtained by removing the circle from A has two connected components, and the resulting space obtained by removing a circle from plus infinity is connected, so they cannot be homomorphic. Okay. However, to give you another idea of homomorphism, if you consider the shapes M and N as letters as subsets of R2, there is a homomorphism between M and N. Why? Because we can deform the letter M into the letter N without breaking it. So we can use bending, twisting, and so on. Okay. But what we are saying here is that no matter how ingenious you are, you cannot find a continuous deformation that takes x into y, or the shape A into infinity, or the shape x into the shape y, or the compact interval 0, 1 into the circle. Okay. Yeah. So last example, the sphere S2 and the torus that we denote by T2, the two-dimensional torus, which is the familiar donut shape, are not homomorphic. Okay. Now, this example is more difficult than the previous examples. Why? Because here we cannot use the argument of removing a point. If you remove a point from the sphere, the resulting space is still connected. And same thing from if you remove a point from the torus. So the argument does not work. So we have to remove something bigger. If we remove the meridional circle from the torus, so it's like if you cut the torus like you cut a cake or a donut, what is the resulting space? The resulting space is still connected. Whereas if you cut the sphere around a circle, any circle actually, intuitively at least, this circle will cut the sphere into two connected components. Okay, so removing when we remove an appropriate circle from the torus, just the surface actually, the resulting space is connected. Whereas if we remove any topological circle from the sphere, the resulting space has two connected components, and therefore these two shapes are not homomorphic. So we cannot deform the sphere into the torus without breaking it. Okay, and the point that a circle divides the sphere into two connected components is actually should be intuitively clear actually, but surprisingly it's a difficult theorem, and it's known as the Jordan curve theorem. Okay, but proving this theorem will require advanced tools from algebraic topology. Okay, so this concludes the list of examples. So I think in order not to make a lengthy video, I will stop here, and I will continue the rest of the section in the next video. So thank you for your attention, and see you soon.